Traditional lighting systems in spacecrafts offer only one constant setting. The continuous bright white light confuses the crew members' biological systems into thinking it's daylight all the time. The body starts to feel stressed. Certain hormones aren't releasing, while too much of another hormone are releasing. Our body has a hormone dispensing schedule that works only when our bodies keep track of the amount of light it's been exposed to throughout the day. It's just like a clock that keeps track of time. This internal clock mechanism is called our circadian rhythm. What if we could have a lighting system on the spacecraft that could simulate the sun's light cycles as if you were on Earth? Is it possible to use this artificial sun to create life? Maybe not life in the traditional sense, but what if we could grow plants? Our senior design team will solve these questions. My name is Farhan. I'm the team lead, front-end designer, and hardware specialist. We have Shafi. He is our algorithm specialist. We have Jittij. He is our network specialist. We have Simmer. She is our back-end software specialist. We are Team Lit. Our motto is to keep it lit. Our teammate Shafi will start with our objectives in the next slide.
Thank you, Farhan. The main objectives for our project are: 1, to create a circadian rhythm routine that can simulate a natural light cycle of a geographic location that each crew member can set. 2, to create a 2-stage plant growing routine where crew members can grow plants or vegetation on the space shuttle with an artificial light source. 3, to create a logging system to restrict access to unauthorized users and offer different access levels. 4, to create a color correction routine that can automatically adjust the light's color if there is any color degradation. 5, to create an intensity correction routine that can automatically adjust the light's intensity to maintain the required intensity. 6, to create a voice control system that allows the user to change the light setting conveniently using the voice commands. 7, to create a graphic user interface to increase usability and improve reliability. To describe the design, I would like to call my teammate Titi.
Thank you, Safi. Now the design. We have our orbital system design for the project here on the slide. The heart of this system is the new use of Node-RED, an open source Node.js backend program that makes programming easier by using a place and link programming model. We can easily create and customize new routings. They call it flows. We'll have server with Node-RED running on the Raspberry Pi 4 attached to a touchscreen graphic user interface. The interface will have a web application which allows users to interact with the system. Raspy, a voice assistant toolkit, will use a USB microphone to capture voice commands and allows users to control the general settings. We'll have 4 lighting zones, which are Minjo Green, Stone Cold, Nora Jones, and the Eagles Henley, all named after the famous UNT alumni, as they are shining lights of our university. One of the zones will be dedicated to plants lighting, while the rest will be used for circuit and rhythm lighting. We use DMX RGB light bars as a lighting source for each zone. Each of the lights will be controlled by Raspberry Pi 4 with Node-RED running on them. All the Raspberry Pi 4 controllers will be connected to different ports on a network switch attached to a router, which allows communication with the server. We'll be using lux sensor to read the light intensity and color sensor to read the RGB values for each of the lighting zones. A Node MCU ESP8266 controller will be used to send the data wirelessly to the Raspberry Pi 4 controller. To describe about the implementation of this design, I want to call my next teammate, Simmer.
Thank you, Chitij. For our implementation, we divided the project into 3 subsystems: the server, the light sensors, and the lighting zones. The subsystems are connected through either wired or wireless interface. This slide shows each subsystem and all the components. First, the server subsystem. We will have a touchscreen graphic user interface which will allow users to log in, select, and control light settings using a web application. Next component is the server Raspberry Pi controller, which will be distributing the commands from the web application to the corresponding client Raspberry Pi 4 through a router using a TCP connection. The server will have a voice control process running to access the GUI using voice commands. Second, the lighting zone subsystem. Each lighting zone is connected to a wired network using a TCP connection to access the database on the server to supply the sensor data and retrieve expected values to the RGB settings. A USB to DMX converter will be used as a connection from the light controller to lights. We will be using DMX protocol system to send the commands to the lights. Lastly, the light sensor subsystem. The Node MCU controller will allow transmission of the sensor data to designated light using the Raspberry Pi's Wi-Fi access point. The controller and sensors will be mounted to a dedicated PCB board. Next, we will talk about our preliminary results. Here is a table that shows our expected results from our implementation, where we have 3 states: requirement, testing method, and what is verified. Once the requirement is implemented, the testing will take place where we'll test our implementation and verify the results to match our initial requirement. This process will be repeated to ensure consistent results. Now I will pass it back to Farhan for our scheduling.
As part of the future development, we will be developing the circadian rhythm routine, a GUI web application, implementing the voice command system, plant environment testing, mobile access for the web application, error detection, and notification system. We would like to thank Dr. Tim Urban and Talia Jurgens from TSGC for organizing and funding this design challenge. Mr. Salazar, our NASA mentor, who helped us get started with giving us NASA's thought process by offering his perspective on designing a project. Dr. Robin, our faculty advisor, for providing us his time, knowledge, patience, and helping us throughout our journey to really make our design a success with his lifelong wisdom in the field of computer engineering. Alejandro Olvera, our lab manager, helped us with the technical support for all of our questions we had throughout this experience. We would also like to extend a special thank you to the University of North Texas Department of Computer Science and Engineering. This design challenge has taught us how to work as a team, learning to communicate effectively, adapt to unexpected challenges such as meeting tight deadlines, and to think critically about all aspects of a project. We work hard to achieve these skills to stay on track with meeting all of our targeted goals listed here for this semester. We look forward to next semester's challenges. We would like to thank all of you for giving us the opportunity to learn, expand, and sharpen our skill. Let's keep it lit. These are our references.
Thank you.
Thank you.